John, thanks for being here today.
Thank you.
And thanks everyone for attending or listening in. We're gonna talk today about building faster AI solutions, and we're gonna talk about the role that software-defined memory plays in there. So I'm hoping that the audience will learn about a very, very efficient way and how they can build and implement artificial intelligence solutions. My name is Maris Bogovici. I work for the Field CTO organization in Red Hat, where I lead a chief of team architects. And I'm joined today by John Overton, CEO of Cove. So John, you're a close collaborator of ours. Why don't you introduce yourself?
Hi, everybody. I'm John Overton. I started Cove a couple of decades ago at this point, and we've been working closely with Red Hat for the last couple of years on a number of projects.
That's great. And today we're talking about software-defined memory. So I think that's a big problem in today's industry, like memory consumption. So tell us, what is software-defined memory and what typical enterprise problems does it solve?
Sure. And Marius, this is my topic, so I can get on and kind of go. So you should feel comfortable to interrupt me when you've had enough. But I think software-defined memory is the last virtualization layer in enterprise computing. If you go back in the history of computing, things evolve in a certain couple of ways. They swing back and forth from distributed to centralized, and they move from big to small in commodification, and then virtualized. You have that with virtualization for compute, for networking, for storage. No one figured out the memory surface of it. That's what we've done. The traditional wisdom of this is you can't solve the problem because of the speed of light, distance of cable. A nanosecond moves, depending on the medium, from 9 or 10 inches up to 13 inches in a vacuum. That's the distance that the speed of light goes. So if you put memory 100 feet away, you're going to get 100 nanoseconds essentially. In fact, we've solved that problem. You can actually do it. So what it gives you is a new way to think about the whole compute infrastructure. You can now think about fully composable infrastructure where you can say, I want this much storage, this much compute, and now this much memory. I can smear it around. It completely transforms the way you think about a data center or an enterprise. Is that a good enough overview, or do you have? I can dive any direction?
No, I think it's really great. And I was kind of thinking of also what are the once you bend the laws of physics, what happens next? Like how do enterprises, I'm coming from a financial services background. I know you worked a lot. We work together with with customers in that space. So I'd be curious, for the audience, some of the practical applications of this solution. Like what do you use it for? Where does it benefit them?
Yeah, this is easy to kind of you kind of really just jump off a building and fly with this, because there's really nothing you can't do once you control the memory surface. So the easy way to dive in and kind of wrap one's mind around it is to think, what if I could have any amount of memory I wanted, anytime, anywhere, anyhow in a data center? So right now, there's this thing called the memory wall that people will often talk about. Well, I build a server and it has so much memory, so much compute, and I build a stamp and then I build a whole bunch of stamps. This would be the cloud approach. And that's, can do a lot of interesting things. What happens if you need more memory than you have in a server? Right now, the state of the art would be to say, well, that's a scheduling problem. I go to the cloud and then I just get a different server. Well, what if you needed memory bigger than the servers that were available? Well, you're out of luck. But that's not the case when you start doing software-defined resources. You can create multi-hundred terabyte servers in literally 200 milliseconds. Like that's how long it takes you to blink your eyes. You can grab memory across the data center and create something that physically cannot be created. And it can perform and act just like local memory. Now that's the easy one. If you look at it, I always like to use kind of pendulum metaphors of swinging one side. So the easy one to think about right off the top of the bat is, what if I could build servers in a virtualized context that I couldn't buy? So instead of buying a 64 terabyte server, which is incredibly expensive, I could compose one. Or if I wanted a 96 or 120, whatever you wanted. The way our software works, it works with any Red Hat delivery mechanism, and it works with any kind of hardware that's supported by Linux. you can then grab the resources that you need. Now that's one side of the pendulum. I can now build better and different than I ever would have imagined that it could do. But you can go the other direction too. What if I could, since I now have memory available at any time, anywhere, what if I bought less expensive, less power hungry, less capable servers from a memory infrastructure point of view, but I gave them memory when they needed? All of a sudden I can cut the enterprise power consumption of a data center up to 50%, half, okay, just by using software. I can similarly create systems that are built on small composable systems and build larger systems only when I need to. So my CapEx goes down, my OpEx goes down. I can swing the pendulum toward ESG if I want to swing that. My time to solution go. I mean, everything can be transformed, and it's done by provisioning rules, except now with memory. Is that kind of a helpful orientation?
It is, and I think you want to kind of like I know because you're working together. So
yeah.
I have to admit that I know the answer to some of these questions. That I'm just kind of asking them for the benefit of the audience. But I think it's true that in many cases enterprises kind of are able to reuse their investment and kind of take some of the kind of older hardware that exists in their data centers, like computers, like machines that are not that powerful, but they still have memory on them, and kind of like breathe a new life in them.
Yeah,
I think.
I mean, of a different. It's a little bit. I mean, as you know, Red Hat and Supermicro did some very extensive measurements on this. Because in the beginning, nobody would really, I mean, it's very hard. Like, we all been trained to think that you can't do this, right? The speed of light, distance of cable, latency, what's your latency, all of these kinds of things. Well, and I know that you know about the testing, but for the benefit of the audience, I mean, there was extensive testing. These are hundreds and hundreds and hundreds of billions of tests that were run 7 times, averaged, and so forth. And, sure enough, all of this is achievable. I mean, you can get remote memory to operate just like local memory, and you can all of a sudden create infrastructure where you don't even have to have the same kinds of memory. So you can have memory targets that have that are 10-year-old machines, and you can hide the latency of those that hardware that's unused. And until you see it, you kind of really, you don't believe it. But we, as you know, there's a very extensive measurements and demonstration that this can be done. So what that allows an enterprise to do is, let's just imagine that you're pushing AI or machine learning, and so you're buying, large memory servers, or you've got a big data analytics division, so you're pushing large memory because, well, that's so much faster. And in the modern context, you have the CPU infrastructure and the memory. It has to be matched with timing on the motherboard. If you go to our approach, you can have targets that are, and we have customers that have targets in deployment, active deployment, for over 10 years. 10 years. And they just, when they are no longer useful for compute and hosts as compute, they just convert them to targets. So every time they buy hardware, they get more memory, quote, for free, because they already have it. It works magic. It just works really well.
That's really cool. And I think the other kind of like the other discussion that I wanted to have was also not only kind of like, because the way, like, I know that there are traditional workloads like databases, data grids, like everything is power and everything is memory hungry. Yep. You brought up AI, and we're going to dwell a little bit in a minute.
Yeah.
But I'm also curious, like, on the kind of, you can talk a little bit about like some of our customers and, practical applications in, areas like fraud detection and like these kind of like, they're really strong use cases.
Yeah. Well, I mean, they're I mean, especially in financial services, you kind of fall over, over logs all the time on use cases. Let's say, and thinking pragmatically, let's say at the end of the day, I have a big surge of performance needs. What I do? Well, if you're in the cloud, you get new servers, you allocate the new servers, you move your workload. If you're in a data center and you have software-defined memory, you have a provisioning rule that just exists. And when the server needs more memory, 2 times larger than the physical server, 5 times, whatever it is, it just gets it. There's literally no intervention of any variety. So any kind of bursty workload that you get, by the way, financial services has just sometimes bursty, right? It just goes away. I'm done, right? And it's a provisioning rule from a system administrator. Boom. So that would be one. Another classic one memory map files. So, people learned in financial services for journaling, where you just have to track the transactionality of your flow. You've got to capture that. How do you capture it? Well, traditional memory, traditional storage is too slow. So people would use memory map files and they would log that. The problem there is you're limited to how big and what that memory map file is. If you use software-defined memory, you can allocate memory map files of any size, and they can auto grow using memory across the data center. It's just magical. Fraud detection. So let's imagine that you want to do real-time heuristics on either a transactional basis or some kind of biometric instance, or any of this. That obviously is going to be a seek against memory. So what's the issue that you face? Well, you go and you do what classically trained system administrators and architects do. You go and you figure out what the best price performing stamp is of compute to memory. You deploy that, and then you cram your workloads into that, and then you scale multiple stamps in there as well as you can. Whether or not you need the performance or you don't, you do it because it's the way you can control the SLA or the predictability of it. What if you didn't have to do that? What if you could just say, I'm going to put some servers there and they will configure in dynamic real time to deliver whatever resource that you have? Well, all of a sudden, things like fraud can be completely memory centric, completely at any scale. In fact, the project that we're working on, as you know, at Swift, which is a shared customer of ours, they're building some of the most sophisticated fraud analytics globally for the entire financial services industry, and that's powered by this kind of an approach.
And I think it bears saying that this is an approach that works for both. I would say traditional workloads directly on running directly the operating system, containerized, what have you, right? I think that's an important, very, very important piece, because containers are typically very constrained.
Well, I mean, containers are almost the killer app. We have demonstrated improving the capacity of containers on servers by 100 multiples. I mean, as in 100x, not 100%. But 100x. And containers are especially useful for working with software-defined memory because they maintain their own locality of reference. If you have, let's say, a high degree of containers on a server, what's the probability that you're using all of the memory all of the time? Well, it's like as close to zero as there is zero. It's not impossible for bursts in very, very small circumstances, but over any sustained period of time, everything goes quiescent and then active, quiescent and active. Well, that's a perfect use case because now you can add dynamic memory that you wouldn't allocate. Let's say that you have 400 containers and you're in an ephemeral environment where you're spinning them up and spinning them down for microservices, which would be a kind of classical use of them. Well, what you immediately do as an architect is you start thinking about how much memory do I have on the server? How many of the containers? What's the workload I'm going to get? What's the probability? How am I going to statistically project this? What's the averaging factor that I want to do? How do I move it down? Okay, you go through all those gymnastics and that's what we're going to do. How about just not? Just apply a software rule that says you get what you need when you want. And it works just like local memory.
I think that's the important part. And I think that's part of our I think that's one of the strengths of our joint work, between Cove and Red Hat, is that you can do it on RHEL with just a simple configuration. You can do it on OpenShift with an operator. You can do it super, super easily. I think that's
super easily isn't loud enough. I mean, it really isn't loud enough. I mean, it's just, you hit, in the case to integrate with us, you hit 3 buttons. Okay, 3 buttons, 41 minutes or less later, it works, and you never know that this virtualized memory is there. It's just OpenShift. It's wicked awesome.
That's really awesome. So let me let me get back real quick, to one topic that we kind of touched upon earlier, because I don't want to end this conversation before going into the elephant in the room, which consumes a lot of memory, which is AI.
Yeah.
So how's AI what do you see? How's the struggle that you see there?
AI is the magic elixir for software-defined memory, or software-defined memory is the magic elixir for AI. So let's just give you an illustration. Let's imagine I'm a company, and I'm going to go big company first, but I think it applies equally to edge computing, small companies, all this. But the big one is dramatically obvious and undebatable. So I'm buying some very expensive data scientists. Let's say I have 20 or 50 data scientists because I'm all in. I'm going to train a model 1,000 times before it goes into production. Maybe I get really lucky and it's 750 times. Maybe it's 1,500, but it's that kind of stuff. So I go out and I go to my management. I say, I got to get the best bang for buck, GPUs or big memory servers or whatever it is. And then you got to source the hardware, first of all, right? And it's designed for this. Now you create a little farm and you create a scheduling system, and you got the 50 people, and they're all doing their data segmentation so that they can fit in perfect parallelism, the amount of data on 50 servers. Now, these are expensive high-end servers, right? Because you got to have a lot of memory. So I do that, and everybody targets, let's say, a 4-hour job. I mean, it can be, every organization does it slightly different, but it's an easy one because you can say 4 hours is, you can spend the equipment in a day. So everybody knows that I got 50 people, I got a 4-hour job. I can calculate this and say, this is when you get the machine, and then I run my job. It's supposed to be done in 4 hours. So the data scientists are spending all their time to make sure that when they get that magic moment, they install all of the data, where it's supposed to, and then they run it. And if they run it, and one of those 50 high-end servers, one of the data segmentation portions is miscalculated on one of the servers, and it balloons up in that computation, it goes above the local memory, well, then it hits swap, right? So no problem. I'm going to buy the best NVMe that money can buy, stick it right in there to cover for this. And that job that was supposed to take 4 hours now takes 125 times slower. That's 19 days. 19 days. And let it hit your back brain. 19 days. Oh, remember those 40 other 9 really expensive resources are waiting. So no problem. Hey, everybody, wait 19 days. Okay? No, obviously nobody does that. So you don't put swap. You turn swap off so that if that happens, you crash your system and you're off in an hour or 2 hours. It goes to the next person. You go back and you think, what do I do to make sure the data segmentation across the 50 servers so that the next time, 7 days later or 4 days later, when I get access to the system, that it's not going to balloon up and then blow up? That's the typical use case. Now, enter Cove. The way it works with, so first of all, so the first thing everybody does as a programmer is you don't use all of the memory, right? I got 3 terabyte servers. What I do is I target 25%, maybe 30% of the memory, on the presumption that, maybe one of those 50 servers is going to double or triple its usage of memory. And then I'm covered. Then I complete my job in 4 hours. So basically the value prop is, as an engineer to management, is buy me the most expensive servers and I'm going to use them 25% of the capability that you bought. That's the value prop, right? And the reason why I do it is because I have to do that 1,000 times. Now, let's imagine that same exact scenario using Cove. So you have, I don't know, your old servers that are lying around that you convert to targets. That same thing happens, something goes up and it goes up 5 times larger than the server, twice as large as the server. And I'm not talking about a byte, or a megabyte above the server and crashing. It goes multiples larger. When it hits it, it takes 200 milliseconds. The process makes a call to Malloc. Malloc gives it more memory, and all of a sudden that server is as large as it needs. I can now push more memory, 2 or 3 times more utilization out of each server. So I'm increasing my accuracy of my ML 2 or 3x. I am increasing the time to solution tremendously because I never run out of memory. I'm getting more bang for buck for the users, or the best return on the data scientists, which is my most expensive resource. And as a programmer, I go to management, I'm saying, yeah, that hardware you bought, I'm actually using it better than anybody in the world. This is better on-prem than you can do in the cloud. And this problem isn't solved by going to the cloud and buying more servers to segment, because I still have to program that ahead of time. This all happens when it needs, right, in real time.
So that's a good point, John. Like, kind of, this idea that, first and foremost, I completely agree with you. Like, time to delivering the solution, I think it's what most companies are kind of like are ailing right now, and that's essentially their bread and butter, so to speak. They don't want to build models. They want to make money from those models.
Go figure. And it's only 1,000 training sessions, no problem, right? Before it goes into production.
But I wanted to kind of talk a little bit about the kind of the hybrid cloud model, and kind of like where does this fit into the, obviously kind of like as companies kind of go to the to these types of as companies kind of look into different ways to optimize and become bursty, and kind of go there, like how do you how does this help, like software memory?
Well,
the resource.
I think that the demise of on-prem computing and the certainty that cloud is going to take over the world is not nearly as clear as people would like to make a claim.
Greatly exaggerated.
Yes, it is greatly exaggerated. I was trying to avoid that maybe because this is recorded. Somebody's going to find some example that doesn't fit this, and it is. But it's great. Let's just go back to imagine where you can go. Cloud gives you lots of convenience and lots of scale if you accept certain assumptions, and then it's fantastic. It's also expensive and sticky. It's not, it's flexible as opposed to necessarily inexpensive. Doesn't mean you can't make it inexpensive, but it's harder. If you can use your hardware more efficiently, you can drive your CapEx and your OpEx down, you can get more flexibility at less cost using something like a Red Hat and Cove software-defined memory deployment than is even possible. And that's a really big, but it's true. Possible. You can't even get this in the cloud. The only way you get this is using this combination of this project that we've been working on for a couple of years. I mean, the hybrid cloud modality, it gives you privacy that you can have a much greater confidence in. It gives you flexibility you cannot get in the cloud. It gives you ability to have cost reduction and power consumption reduction, control over your own resources, your own scheduling very conveniently. This is game changing. And I hate to use that word because it's so overused, but it really is. You can do things at home that you couldn't do before.
Cliches are cliches for a reason, they say. So, it's like, so it's definitely, I would agree with you. It's definitely a complete different experience. And speaking of game changing, like, what do you see kind of as the kind of like the future? What's next on the horizon? What kind of like, what do you see kind of the innovations in this space? How is it evolving?
So I have lots of opinions on this. I think that, as I've said in other, public, contexts, right now there's a big move for memory-centric computing, right? People say, oh, it's here, it's coming. And, one variant of this is CXL, that's being led by a number of the chip manufacturers. We've been shipping product for over 10 years that is on the roadmap to be delivered in the next several years, undeterminedly, from CXL. It's there, and it's only software, and it works only with any hardware that exists in the world that's supported by Linux, as opposed to an upgrade. So I'd say the first innovation that we've got to think is, as we move to memory-centric computing, we don't want, if ever we have ever learned anything, we don't want to move to new hardware platforms. Every innovation doesn't need new hardware. It shouldn't. It should need new software, more effective software to run on any kind of hardware. You want a competitive hardware environment where you can use anything. So the first move is, I think you're going to see a lot of different interconnects that are going to hit the marketplace. I think you have Slingshot, which is an HP Cray kind of approach. You've got Rocky and Ethernet. You've got PCIe Express as a potential. You've got InfiniBand, and from NVIDIA. You're going to have more of those. And as you do, you're going to get into something we've seen that happened for generations in computing. Someone's going to say, if you buy all of my hunk of stuff, I'm going to give you a great deal. It won't be sticky, trust me. And then it's sticky. If you go the approach that Red Hat has and the way that Cove has, you should be able to use any kind of hardware you want. So the first thing is, I'd like to try to skip a generation and not build proprietary systems and go right to the software part. That'd be number one. Number two, I think we got to leave the inherited wisdom that that performance is determined by processor. It isn't. If you're scaling AI and machine learning for genomics or LLMs, memory needs scale quadratically. I mean, just let it hit you. A big supercomputer that you can buy to power the supercomputer takes 40,000. A power center capable of powering 40,000 homes. Now, every time you're gonna increase that, what do you need to do? Oh, just buy more power centers. More like villages of power. What you got to do is be much more clever, and it's not just hardware; it's the software stack. I think that's getting ready to happen tremendously. I think the next very big push is I do not think that cloud all is said and done about what's going to happen with the cloud. I think things are going to move increasingly back, and this has been the case for the history of computing. You had mainframes, and then you had workstations, then you had PCs, then you had clusters of PCs and supercomputers. It goes back and forth. We're just at the beginning of it swinging back to where you can do things locally because of latency. Going up and down a cloud is 200 milliseconds. So you want to have a smart city? What are you going to do? Blink your eye. Next time you're driving in car, close your eyes and open it. Take your hands off your wheel, close your eyes and open them, and see what happened in the car. Imagine that's happening with 5,000 cars across the city. That's the speed of light going up to a satellite and down. You need to have that local. To have that local and to have machine learning, you have to have flexible memory. All of this is just getting ready to happen. It's a really exciting time.
That I agree with you. It's really, really exciting. Any kind of thanks a lot for this conversation. Any final thoughts, like anything that you'd like to kind of bring up and think
Yeah,
about?
I would. I think especially in financial services, sometimes people want to wait until things are, older. I'm trying to use terms that are value neutral. This is not something to wait. AI and machine learning are real. You take OpenShift and you put software-defined memory with Cove on it. You can do things that literally cannot be done anywhere else. It's a huge opportunity to get ahead of everything, and it's coming, and it's being used in the world for the backbone of the financial services right now.
Got it. No, I think that's a great way to kind of sum up our conversation. John, thanks again for being here. Thanks a lot. Thank you again for this conversation. Thanks for being a great partner of ours.
No, thanks.
And for everyone here, feel free to follow up, us, follow up the other resources that you find. Follow us on LinkedIn if you like. We're here.
Please reach out to us whenever you need, however we can be helpful.
Exactly. We're here to work together with you. Take care. Talk to you soon.
Bye.